Yes.
Okay, wonderful. Oops, sorry, perfect. Okay, ready for part 2. As I said in the beginning, in this part is a bit different because I want to outline some recent research directions. So I have picked 4 topics which are quite new stuff, which could be interesting a little bit for everyone. And these 4 parts are also independent of each other. So if you don't understand some part or get lost or something, just wait until the next part starts, and then you can have a fresh start. So you don't need anything. Just the talks are independent. Okay, yes, I will start with a bit more robotic stuff. So the connection between topology and robot kinematics, because robot kinematics is something that's also studied a lot in engineering, and this is some formalism that this should be connected to, and there are some authors who try to establish some connection of TC with these more hands-on things in robotics. So this is after works from Peter Pavicic from 2017 and 18, and there's also some work by Murillo and Wu, published in 2017 as well, and which is tackled similar question with a slightly different approach. I will mention this later maybe, and I will just give an overview of the construction. There are not many results yet, but just to kind of how to approach things. So let's again consider a robot, which is kind of given as maybe a robot arm or some linkage or some really robot running around or something, which has an end effector. That maybe it has some device or some sensor, or maybe let's imagine a robot arm holding a screwdriver, which is doing something, which is manipulating, measuring something, but which is kind of, there's one end effector that we are actually in its position we are interested. And the point is really, if we want to study these problems like having screwdrivers, we don't care about the position of the arm, we just want the screwdriver to be in place. So we just consider the position of the end effector and don't care about the configuration of the robot, and it can do whatever it wants. So this is something we need to formalize. So the screwdriver example here, and so there are many other examples, of course, where we just want to study this end effector. And so the idea is kind of, when we do this motion planning, we actually don't need for these things motions between all possible positions of the robot, because the positions of the robot don't matter. But we want that we have, if the robot is in some position, we just want it to get in some other position. We don't care about the precise position as long as the end effector is in the right place. So we just need to get it somewhere where the end effector is really in the nice position. And this is something we want to formalize then. So we don't need motion planning for all configurations of the robot arm or of whatever we study, and to really get this formally done. So to get this done, I introduce some formalism that's actually really also used by robotics people in kinematics. Namely, the main first simple thing is with each of these robots, or some robot manipulator with some end effector, which is doing this stuff, we associate 2 different spaces. So the one space is the configuration space, which is just, so it's not to be confused with configuration spaces in the first talk. So this just means the possible configurations, or in the sense of positions of the robot itself. Secondly, we consider W, the workspace. This is the space of possible positions of the end effector, which we consider separately. I will give you an example in the next slide. But this is 2 different spaces. And then we have, together with these spaces, a map which is called the forward kinematic map. So this is forward kinematics, or simply called work map by others, which is a continuous map going from this configuration space to the workspace. So with every configuration, we associate the position that the end effector has in its workspace when the robot is in this configuration in the configuration space. So this is something that is really studied in there. Very simple thing. Here's an example. So here, this is a robot joint, so robot arm with these 2 bars here, and with a joint here.
Slide is stopped.
The slide is stopped.
Oh, yeah. No, okay. Okay, let me stop sharing and do it again.
Okay. Yeah, it works. Yeah.
Wonderful. Okay. So this is a simple example of some mechanic or some robotics, a very, very simple example. This is a robot arm which has a bar here and a bar there. And we're just basically we have joints here. So this bar is allowed to rotate here in the XY plane basically, and we have a rotation here which is kind of in the it's a vertical circle in that sense. And what we're interested in is the position of the tip here. So we can assume that there's some sensor or whatever. So we are just interested in the position of this black dot. So however the thing is positioned, we just need to get it somehow in a position where the black dot is somewhere where we want it. This picture, again, I have no copyright, but I tell you where I stole it. It's from Pavlicic's work, A Topologist's View of Kinematic Maps and Manipulation Complexity. There are also many more examples studied in there of these robot arms and joints and whatever. And if we take a look at the space that we have here, so the space of configurations, that classifies all the positions of the robot. This is, we have one circular axis here, we have one circle there, so and these two determine the robot's position, so the configuration space is just S1 times S1. The workspace is now constructed in this way. We see that this black dot here will always be on the 2 sphere, so on this sphere here. So this workspace is just S2. And the forward kinematic map is then something which goes from S1 times S1 to S2. So with each of these positions of these two joints here, we associate this point on the 2 sphere. So this is just what this forward kinematics does. The more complicated thing now is so-called inverse kinematics, where we want to go to the other direction. So what we would like would be to have a continuous map from the workspace to the configuration space, which kind of continuously associates with each position of this end effector some configuration which does this nicely. So this means we want, which corresponds to this end map, of course. And this is much harder to get. So this would be a continuous section of this forward kinematic map F, this work map. So we want to go back and how do we need to configure the robot to end up at the position that we wanted? To have the sensor end up at the position that we wanted. But it turns out this is easier said than done. This is a kind of old theorem from Gottlieb from '86, and this is basically also he investigates the connections between robots and topology and robot arms basically. Namely, if we're in a situation that the configuration space is a torus, so S1 to n copies. And we have a work map as workspace. We consider either S2 as before, or SO3, or SE3, the Euclidean group in rank 3. This is basically a group which formalizes rotations like an SO3 and translations. So this is some, if you don't know this, it doesn't matter here, but this is also something which is quite natural in robotics, because rotations, translations for mechanical objects, this is what we want to study. And of course, SO3, we have a 3 frame, so an orthonormal basis for R3. So it's kind of, you can see this as the positions of the axis of the robot as a 3-dimensional device. So this is these are quite natural things that occur. And the bad news is that a continuous map from the end torus into one of these things does never admit a global continuous section. And this is something that's purely topological. So the proof is really using, I think, playing around with homotopy groups or cohomology groups, but this is just nothing very wild. But this is something that really follows already from topology. So this already shows that this inverse kinematics problem is not that simple. And this we want to now go back to the motion planning problem. And again, so we want to study this motion planning problem now with respect to these ideas in mind. So the abstract problem would be now, so given in some configuration C, in this configuration space curly C, and some end effector position W, we would like the robot to move from C to some position where we have, so let's call it C prime, where f of C prime is W, so where the end effector has the position we want. So doing this again abstractly with topological spaces. So we have the situation where we now forget about robotics. We take two path-connected topological spaces, C and W, and take a continuous surjective map. So this generalization of this forward kinematic map from C to W. So given the configuration C and some W in W, we want to find a path, so continuous map from 0, 1 to C, which starts at C and which has the property that f of the endpoint is W. So this is what we want. And if we have this problem here, then again, we can ask this question, like, can we do this continuously in some sense? And for this purpose, we need to introduce a further map. So again, we have pi as in the first part denotes this path evaluation map. So we go from PC to the C times C, which evaluates a path in C at its endpoints. And then we compose this map with the identity on C times the kinematic map. So this really takes some path and evaluates in the first component the starting point, and in the second component the end effector position of the endpoint of this thing. And what we then want to solve this abstract problem here is really local continuous sections of this map. So this is really what we want to study here. But there's a very clear technical flaw. Namely, the problem is if this map F is just continuous and surjective, this might not be a fibration, then this map pi F will not be a fibration. This was really crucial to what we did before, namely these techniques for sectional category. So they might be non-available. Just if this is not a fibration, like these things with lower bounds, upper bounds, and so on, they all rely heavily on this fibration approach. So we can define a number in this way, like we can define like a minimum number of local sections, but these techniques might be non-available, so it might we cannot just work with these maps that easily, and this is also the main problem why it's so hard to compute also examples for this, because all the techniques fail us. Like this problem with pi-f not being a fibration, there's another approach by Murillo and Wu, which I don't want to talk about today, which is very roughly where we don't search for sections of pi-f, but for sections up to homotopy. So just we can deform into sections, and then you can really use also you can generalize the sectional category to this situation when you search for homotopy sections. This works, and then you get a lot of topology on your hands. But of course, it's a problem because here we talking, if we really want to model a mechanic situation, we want to be something which is starts at a precise position and goes to a precise position, and we don't want to something up to homotopy, but we want it to work out well, these motion plans. So this is the Murillo and Wu approach, then works in this one way, but has this flaw in the other way. What I'm now going to present is this Pavicic approach. This is now basically generalizing this notion of TC. So again, we have some map from C to W where we model these spaces, so continuous and surjective, and take this map pi f, which basically composes this path fibration with f. Then we can just define TCF in the following way, and this is something which is highly non-intuitive, but this is something I can also tell just that this works. We take the smallest n in n such that, and now we can kind of find an exhaustion of C times W by n sets. So really like this whole, full exhausting sequence of these sets, such that each of these individual sets is closed, and such that on each of the difference of two adjacent sets. So we just take the new part and take out the old part, such that we can kind of, then on these things here we have a continuous section, such that, really this section property holds, so pi f composed with Sj is the inclusion. So that this is really a local, motion planner with, or not really motion planner, but with respect to this endpoint here. So this is a construction that really work, that you can define, and that you can a bit work with when f is not a fibration, which I will not go into details because this would be quite complicated. But the good thing is also that this was also shown by Pavicic, that this generalizes the fibration approach, and namely if we have the case that f is indeed a fibration, and this additional technical condition that W is a metrizable absolute neighborhood retract, it's almost the same as a locally finite CW complex, so in a nice space, then it's all fine. Then TC of f is indeed the sectional category of this pi f, which is then a fibration. And a very special case, if C is equal to W and f is the identity, we just get back the old topological complexity. So this really works well with this framework in this setting. As this also holds for Murillo and Wu, that this kind of gives back for the identity the old topological complexity, but this has, as I said, this has other flaws. But this is the way that Pavicic can do this. So the aim is now, and this is something that, this is the way this is what you could use this for. That you want to really compute TCF for really concrete examples from actual problems in kinematics, where you really have some map from the torus to some reasonable workspace or something, or to some computation space of explicit linkages. And then, of course, because we're really talking about concrete robotics here, find explicit motion planners. So all the estimates don't really help if you can't really find solutions for your problems. So we want with few domains of continuity. And in this example in the picture I just had with the bar with two joints and the effector on the sphere, Pavicic has then really computed that this TC of f is at most 4, and he not only computed this, so he really constructed 4 domains where you can really write down the motion planners in this example. Okay, and this is all I wanted to say about this forward kinematics and so on. So this is the idea is really, this is what Pavicic has done for many examples, to really find explicit motion planners for these examples and work with them. And this is something, Pavicic has started doing, and this is still an active field of research. So since this is only a few years old, there's not that much research on this yet, but this is how you can get really to the thick of it in robotics. Okay, second part. I want to talk about something called parametrized motion planning. This is also an idea which is very fresh. It's from this year, from Dan Cohen, Michael Faber, and Shmuel Weinberger. Namely, if we have these motion planning problems in some practical situations, one might do motion planning problems in which depends on certain parameters in the space, which might change occasionally. And to give you an example of this, let's assume we have a robot in a warehouse which is moving there, and which contains shelves or where items are stacked up or some things are standing around, but these things might be moved. They might change from one day to the next or from 1 hour to the next or something. And what we of course would want, but then that the robot is able to cope with this and to know when, if from the new position, that it will kind of again find its way and do this motion planning, but somehow really do this in a reasonable way. So as like if the shelf is like 1 meter next to the position where it was before, that the robot will behave similar to what it did before. So of course there we would have some feasibility or some plausibility of the motions of the robot, and some we want it to behave halfway predictable. This is kind of the main idea underlying this construction. Another example would be, that's by Michael Faber, which I also like. We have a submarine in the ocean, so a warship or something, where there are mines in the ocean. And these mines might be kind of floating around in the ocean, and of course they're kind of changing positions. So like if like an hour later or something, they might have floated somewhere else, and so you need to coordinate submarines that they don't crash into these mines. So this is a really general thing that you can find many other examples, but this is something that's really that occurs in real life situations. So the main just got some sound. Can you still hear me? I got some.
Yes.
Yes. Yeah, we can still hear you. I think somebody made a comment.
Oh, okay. So, okay. Okay, sorry. I just thought it was some strange sound. Okay. Okay. Sorry. So what these two cases have in common is it's the same spirit here. We're doing motion planning in some space, and then take out a finite set of points. So let's say some set Q. But of course, if Q changes a bit, if these points change a bit, we want to keep our motion planners somehow stable, or at least as stable as possible as we can if we change the positions of these points. And this is something we can also nicely formalize. First of all, this motion has somehow been this thing has somehow been studied before, like for motion planning with obstacles. Oh, sorry for the typo. Namely, we have a nice fibration here, the Fadel-Neuwirth fibration. So this is a result of very classical about configuration spaces by Fadel and Neuwirth from 1962. Namely, if we study these configuration spaces, which are again defined as in part 1, so kind of tuples in the space, so in X to the certain power, so that no 2 points do coincide, and no 2 distinct points do coincide. In the case that we have a manifold of dimension at least 2, then we have a nice map. Namely, if we have the configuration space of X of m plus n points in X, we can just take a projection map to the configuration space of m points in X, simply by forgetting about the last n coordinates. So this is then really indeed a fiber bundle. This is a result of Fadel and Neuwirth, and the fiber is then homomorphic, of course, to, so let's say if we here fix some points, x1 to xm, if they are fixed, then they are of course kind of taken out, and the additional condition is now that the remaining endpoints here, that they do not meet one of these points. So this fiber will then be, the fiber is just the x and the complement of qm, where qm is then some set with m elements, and the configuration space of n points in this set, so that they don't meet any of these n points. It turns out that kind of this, if we change qm, this stays really homomorphic and so on. This is of course non-trivial, but this works. But this is basically the thing we are having here. And so now this is the idea that in this way we can now see the space of the fibration, this f of xm, as parameter space, because this is really here the parameter of our motion planning problem that we would have here. So to do kind of collision-free motion planning problem with respect to m fixed obstacles in this configuration space, and to have, so this would be n different robots moving in X and should not meet this QM. This would then maybe do motion planning inside a fiber of this fibration here. And of course, we're staying inside the same fiber. That's the point here. Now,
if I can ask, well, essentially what you have like m mines, essentially, and like let's say n is one submarine. Yes. In each fiber, you put all these mines at a point. You consider them also as moving robots, and you just consider it each fiber. So then the mines would say still in each fiber.
Yes.
You try to. Okay. Yeah.
You consider them as still, as fixed. So they are not moving at this point. They might change position, but during the movement, they stay where they are. I mean, of course, it would be interesting to see what happens when they are moving as well. But it turns out that this is technically even more complicated. So this is kind of the first step, and this will be the next thing to investigate. This will be
okay. Right. Yeah.
Okay, so inside the fiber, the obstacles are fixed. That's completely correct. So what we want is a notion of TC, or some generalization, which kind of stable under changing fibers, but just staying in one fiber, as I said. And this is something we now will next formalize. And this is what the main content of Cohen-Faber-Weinberger, and some proof that I'm doing very fresh stuff. This is from September 2020. So this is really new. So we start very general. We have a fibration, which is kind of modeling. So B is then seen, the base spaces here as our parameter space interpreted, and the fiber is supposed to be path connected. So this is, like we had this motion planning, we need path connected space. So, okay, as an abbreviation, I denote the unit interval by I. Okay, then first of all, I consider the pullback of P by itself, which means I take all pairs of points in E, which are lying in the same fiber. Since I do motion planning with only in the same fiber, I just need pairs of points that lie in the same fiber to do this motion planning problem. So this is just a simple pullback, and then we need the corresponding path space, and this is just then defined like this. E to the I index B, we take the space of all continuous paths in E, such that the image of the whole path lies completely within one fiber. So all paths which just map to one single fiber. This is the space we need here. And it turns out then that if we just take this path space and this pullback space here, the restriction of the path fibration to this here is indeed, again, a fibration. This is not trivial to see, but this, you need the P as a fibration for this, but this is how you get that you get a fibration, and then you can guess what we're doing next. We take the sectional category of this fibration. So this is then denoted by the three authors by this TC and then P in this square brackets here put in there. So you take the sectional category of this, and just to remind you, I'll just write down the nice explicit definition. So the smallest number, so we can cover this pullback space, so pairs of points in the same fiber, then we can cover this everything by n open subsets, such that over each of these subsets we have a local section, so a motion planner, which of course now depends on the parameters that are contained in this open set. So this just means we want the smallest number so that we can have the stability under parameters. And yeah, this is the definition. And then you can, of course, ask what happens. So first of all, we have a fibration with path-connected fiber. And as I said, this somehow generalizes this motion planning inside the fiber by including these additional parameters and to make the parameter dependence included there as well. And first of all, you can observe that TC of the fibration P is always bigger than or equal to TC of the fiber, which is not really surprising. And it turns out the difference between these two can become arbitrarily big. So for every natural number, you can find a fibration where this difference becomes arbitrarily big. And we will even see an example of this in a few slides. Then is a situation where we have kind of the opposite, where they will coincide. If we have a principal G bundle, then the TC of the fibration is just the TC of the fiber of G. And as we've seen before, this is then simply the Lussner-Stiermann category of G. So this would be kind of the other extreme. Here we really, so parameter dependence doesn't damage it. Then we also can find upper and lower bounds, which are constructed also in the same way as the upper and lower bounds from the previous section for the classic TC are constructed. Namely with a bit more restrictions. So if we have not a fibration but a fiber bundle, and if E, F, and B are also base fiber total space or CW complexes, and the fiber is R connected, then we get this bound from above by twice the dimension of the fiber plus dimension of the base plus 1 divided by R plus 1 plus 1. If you compare this with the original upper bound for TC of the fiber, the only difference is this summand here. This plus dimension of B is additionally in there. And but the rest, if this wasn't there, this would just be the bound that we get for TC of the fiber. So you can really see this is kind of so the including parameters at most worsens this by the summand of dimension of B over R plus 1. This is kind of how bad it can get. The lower bound can then be done in terms of cohomology. And if you recall, we had this zero divisor lower bound, so we had this kernel of the diagonal that was involved there. And there's a similar bound like this. This is also constructed in the same way and derived from this results of Schwarz. We take the diagonal, but this time not as a map into E times E, but into this pullback. Of course, yeah, the diagonal consists of points lying in the same fiber. That's trivial. So we have this is mapped into the pullback, and then it turns out that the TC of the fibration P is then really bounded from below by the cup length in the pullback of in the kernel of the pullback of this diagonal. So some kind of parametrized zero divisors, or however you want to call this. But this is then again, this is the cup length in this ideal plus 1. So this is constructed in the similar way as before. Okay, so now let's get back to our Fadel-Neuwied fibrations, because they are the kind of most natural examples. And Cohen, Faber, and Weinberger, they studied this for Euclidean space, so for the very most simple situation that you can have on the natural ones. And we want to study this vibration that, again, kind of parametrized by this M obstacles. So this was, motion planning, collision-free motion planning for N robots with M mobile obstacles. But as we just said, they are still during the movement. So we consider these robots as still, the obstacles as fixed in the movement, but might change over time between the movements. Okay, this was then really computed by Cohen, Faber, and Weinberger. They had some situations, not everything, but most of it, or not most, but one half of it actually. If we take odd-dimensional Euclidean spaces, so odd-dimensional spaces of dimension at least 3, and then we have at least two obstacles in at least one robot, then we get that the TC of this vibration is 2n plus m. So here we really have this m of the parameter space. This is really going into this TC. And similarly for mn in n, we get that in the two-dimensional case, this space has the topological, this vibration has the complexity 2n plus m minus 1. So also a slight difference here. So the interesting thing is now, of course, how it behaves with respect to the fibers. The fibers are these configuration spaces where you need to remove some points. And this is something that's also known. So the fiber of this vibration here would be the configuration space of Rk minus a subset with m elements. Of n points in this space Rk minus Qn. So this is the fiber that occurs in this vibration, and this fiber also has been studied in several cases. There was a result by Faber, Grant, Juswinski from 2007, namely in 3 and 2 dimensions. If we remove m different elements from R3, the TC of this configuration space here is 2n plus 1. So that might be a slightly surprising thing. So it doesn't even depend on the number of points that you remove here. And here it's almost the same. In two-dimensional space, if we remove m different points, the only difference is if we move 1 point or if we move more than 1. If we move 1 point, we get 2n, and more than 1, we get 2n plus 1. But again, this doesn't depend on the number of points that we're actually putting out there. And comparing this with the previous result, where this m really occurred in the formula, we get that the difference between the TC of the vibration here and the TC of the fiber, this is really m minus 1. And so you can see this becomes arbitrarily big if n becomes arbitrarily big. So if the number of obstacles that we are studying in this problem becomes arbitrarily big. So here in the case of the 3-dimensional Euclidean space, which is also the most natural from the point of view of robotics. So this is, this is how you can see that this parameter dependence really increases the difficulty of this motion planning problem. Okay, so much for this parameterized stuff. And the third thing I want to talk about is so-called geodesic complexity. And this is related to what we kind of quickly discussed in the break. Namely, there's a simple problem, and I've included a picture. Topological motion planning has a problem, namely the paths that we associate with anything. They are just some paths, some sections of this vibration, but we didn't care about the kind of structure of the path, and they only depended on the topology of the space. But we didn't take a look if the path was good, if it was doable. And then, of course, we could have situations like this, where a robot kind of unnecessarily makes some twists and turns and goes around here and so on. So yeah, it's got flair, but this is really not feasible and not really usable. So to implement things, we would of course like to know what can we find simple paths. So what is the thing that we can then put here with the additional restriction that we get if we demand that we have simple paths, and what happens if we put this on top? And this was done by David Reccio-Mitter, also work from 2020. So this is what I just said. So the problem is we might have motion planners with few domains of continuity, so which have the lowest number possible, but which consists of paths that are just very inefficient and so pointless for practical applications. And so the idea is kind of the additional requirement that all paths should have minimal length. So we really want to have them as short as possible. And the question is now, how many domains do we need in this case? So this is also something that we should then study and decide what's important for us: fewer domains of continuity or more efficiency. And so we do this in metric spaces. So this is the most general construction. Everything, in the Riemannian manifolds, you probably know how minimal geodesics look like, but I will then give this very general description. We start with an arbitrary metric space and some rectifiable curve, so some curve whose length we can compute. Then we call gamma a shortest path. If its length, L of gamma, is just the distance between the start and end point. So this is just very simple. And then we have the notion of minimal geodesic, which in many manifolds also we see as geodesics as curves of constant speed. And this is the way we formalize this for metric spaces. we call gamma a minimal geodesic if we have some constant lambda such that the distance from gamma T1 to gamma T2 is proportional to just the difference of the intervals. So yeah, to the absolute value of T1 minus T2. So this is how we get the distance here. And it's then easy to see that each minimal geodesic in that sense is indeed the shortest path. And yeah, then we call, additionally we call some metric space geodesic if there always exists such a minimal geodesic from any point x to any point y. So there might be more than one, but if there always exists some, so for example, in complete Riemannian manifolds, we have this situation, but this is just the general thing that we demand. So the idea is now that we will only study motion planars on domains. So A is a subset of x times x from A to the path space of x, for which S of xy is the shortest path from x to y, and this for all points here in this domain that we're studying. So this was then done by David at Reggio Emitter. So if we have a geodesic space, so we have these minimal geodesics, we then define Gx to be the space of all minimal geodesic paths in X, so as a subset of the path space, and then consider the restriction of pi to this space of geodesics. So from Gx to x times x, and again evaluating the path at its endpoints. The geodesic complexity is then given by the following number. We do a similar construction as before. Do you want to ask, like, can we decompose our x times x into how different sets we can decompose it? So the smallest number n, such that we have a decomposition into n sets, we call aj here, such that each of the aj is locally compact, and such that over each of these aj we have a local section of this pi, but then restricted to geodesics. So we can connect each 2 points by a geodesic and have this complicated thing. I've forgot to add the requirement. This is continuous, of course. So all these SJ should be continuous maps. That's important, of course. So this is the geodesic analog here. So first of all, this is what David observed. We would get the same number if instead of Gx, we would just not take minimal geodesics, but shortest paths in X. This wouldn't change the number at all. And so we decided to take this minimal geodesics because technically it's a bit easier to handle. Secondly, so if we take minimal geodesics and Riemannian manifolds, this really coincides with the usual definition. So if you're not familiar with these metric space constructions and you want to think about your differential geometry, think of Riemannian manifolds. That's fine for today. So then we really get minimal geodesics. And first of all, next, if X is an Euclidean neighborhood retread, so for example, in Riemannian manifolds, then we of course get that the topological complexity is at most is lower than or equal to the geodesic complexity. I mean, if we have geodesic motion planars, then we have motion planars in general, so this gives a lower bound. Okay, so again, we have the same technical difficulty that we had before in this kinematic approach of Pavicic, namely this restriction of this of pi to geodesic paths in X is not a fibration anymore. So again, we cannot use general results on sectional categories and use the lower and upper bounds and so on. So this is really, again, hard to estimate. So let's take a look at some cases we can consider. First of all, the spheres can be computed easily. We can then see that GC of Sn is TC of Sn. If we take Sn, with respect to the round metric, so the standard metric on spheres, this is we've already seen this basically because the motion planars that we had in part 1, these were either connected by minimal geodesics or by semicircles, and they are of course minimal geodesics. So these motion planars were already geodesic, so we can just copy the proof here and get the this because everything was geodesic already. Then one can show it's not that trivial that on projective spaces we also have the same, that they coincide. So on real projective spaces here. And so for these real projective spaces, this is also something that the motion planners, because I sketched the idea, and you can kind of construct motion planners which you can deform into geodesic motion planners. This is kind of, you can also do explicitly with motion planners you have in the TC case. So you get that GC has this property, this coincides as well. But the question, of course, and this is what we would expect, like intuitively, because not always we have these nice minimal geodesic motion planners. Are there examples where there's no equality, so where TCX is really lower than GC of X? And then if so, and the answer to this will be yes, how big can this difference become? So how much can they really differ? And it turns out by a lot, as we will see soon. But first of all, we consider kind of an approach of how to handle the geodesic complexity. And the crucial term here is the cut locus, which is also, most of you might know from Riemannian geometry. So for metric spaces, we can define this easily, say, if we have some point x, then the cut locus of x is just the space of all points such that between x and the point are more than one geodesic. So 2 or more, we don't care. But this is, of course, if we have a unique minimal geodesic, this is a good situation for our geodesic motion planning, because then we know what this looks like. But here we get the complexities. Then I define a set which David is calling the total cut locus. Namely, we take, basically the union of all the cut loci. Just the union of all x times cx. So this is kind of basically all pairs of points that we have inside the space x times x, between which we have more than one minimal geodesic. So this is kind of the thing that troubles us. And it turns out that if this is quite easy to see. So this was first observed by Blaszczyk and Carrasquel-Vera in a paper also dealing with similar issues, and then by David Riccio-Mitter, that on the complement of this total cut locus, there we have a motion planner which consists of geodesics. And this is, of course, easy to see, because just if we have a unique minimal geodesic, we just define our motion planner that way. So S of xy is just defined as the unique minimal geodesic from x to y. This is well defined on the complement of C. So there we don't have any problems. We can just write down this geodesic motion planners and we're fine. So the whole difficulties of the geodesic motion planners are part of the cut locus. This is really what makes the problems here. So it is total cut locus, so basically the union of all cut loci in a certain sense. This is where the difficulties come in. And so I formulate like this. So geodesic motion planning is completely determined by the total cut locus. And the problem is, as those of you who know about Riemann geometry also will know, that cut loci in general, not only the total ones, but cut loci can be very, very complicated. And in general, there's very few explicit results or some about the structure of cut loci. They can become really ugly sets. There's basically, I think, one of the few, or the only case probably, where you can really write down cut loci explicitly and do it in a very nice way is for globally isometric spaces. And this is something I'm currently also working on with my colleague Maximilian Stegemeyer from Leipzig. We are working on the geodesic complexity of globally isometric spaces, and this becomes already complicated because the cut loci are determined by representations of Lie groups and a lot of theory coming into there. So this is some thing is not that easy. And the approach that David has then done in his paper was that he has derived lower and upper bounds for GC of x, where he kind of used stratifications of the cut locus and so of this total cut locus. And there are some cases where you can really write down some where you can stratify the cut loci in a nice sense. So sometimes you can stratify this into totally geodesic submanifolds, and some really few examples. But there are this is the idea. We decompose this total cut locus into some slices that we can handle. And as you might imagine, this is, of course, not that easy, and there's only very hard to say things in general about this. But David has computed some examples, and to see that it's already there are already complicated things happening for simple spaces. Namely, the first example is the 2 torus. First, if we take the 2 torus with a flat Riemannian metric, so just as a quotient of R2 with the metric inherited. And on the other hand, we can study this metric. So this was GF, and we have the metric GE, which kind of comes from the embedding of T2 into R3, as we know. So it's just as Euclidean metric as this nice torus as we would imagine it. Then it turns out that the GC of the flat metric here on the torus coincides with TC of T2 is 3. So in this case, it doesn't become more complicated. But if we take this Euclidean metric, GE, we get that GC of this 2 torus is 4, so already one bigger. So here we can already see the difference between two it's not very exotic metrics. This is metrics they are kind of studied every day in some sense. And so this is, there we already have a difference. And David has pushed this even further, namely David has shown that for every k and n, we could find a closed Riemannian manifold such that the difference of the geodesic complexity, I've also included here the metric in the notation of mg, minus the topological complexity is bigger than, is at least k. So we can become arbitrarily big. And you might ask, of course, now, like, how does this Riemannian manifold look like? And it turns out it's surprisingly simple. We can always choose M to be the k plus 3 sphere. We just need a suitably complicated metric. So we can there already really do some explicit twists and turns with the metrics there to get some really messy metric. So this is kind of, I found quite surprising that you can kind of, make, simple spaces very complicated.
Is this sort of a generic thing? Like if you take a random metric, then the geodesic complexity gets very big because this cut locus gets very complicated? Or
That's a good question. I don't know. So what David is doing is to really explicitly construct some metric with respect to this K, and to really to kind of deform and twist and turn and so on. But it's a good question if this is how the distribution is among the metrics of GC would be. Wow. It's a very nice question, but I have no idea.
Okay, thanks.
Okay. So this shows that even on the spheres we can make complicated things, and not only that, we can even take a simpler space. We can take Euclidean space, not the Euclidean aspect of metric, but we can just take R to the k plus 1. And David has shown that on every R to the k plus 1, you can find some metric GK such that the geodesic complexity is k plus 1 or bigger. And of course, TC of the space, the R to the k plus 1 is contractible, so TC is simply 1. So we can also make a mess here by just perturbing trying metrics and making them complicated enough already on the space here itself, on this space R to the k plus 1. Okay, this is all I want to say about this geodesic approach. So there's still.
I have a small question.
Yes.
So, like these constructions, they seem to rely on the fact that you choose a very high-dimensional Riemannian manifold. So does it like scale in dimension? So for low dimensions, you would still have an approximately the fact that the difference is very small, or just.
I don't recall.
So for example, RK plus 1, like you have a k plus 1 dimensional object, and the difference can be quite big. But for small dimensions, it's also very terrible, or?
It's a good question. I don't recall actually. Sorry, I would have to read up. No, I can't tell you yet.
Okay, that's fine.
Yeah. Yes. Yeah. Yes. Yes. Ooh. Okay. Mhm. Ah, thanks. That's yeah. That sounds interesting. Huh. Okay. No, sure. Okay. So this was the geodesic part here, and the fourth and last part is entitled spherical complexities. About again the different aspects. And before, I have to give you a warning because of this part. This is special because I'm doing shameless self-promotion. This is my own research. And I want to talk a bit about this construction because I think it also fits in here nicely because it's a different aspect. This is by 2 articles of mine that I've mentioned here. So I will go back to this critical point aspect again. This is a theorem I had before in part 1 already here on my slides. The classic Düsseldorf-Schniermann theorem. So the number of critical points of a function on the Hilbert manifold, which has this Palais-Mail property and this differentiability property, is bounded from below by the category, by the Düsseldorf-Schniermann category. Okay, this is now just a very general thing. So this is the number of critical points. But sorry, the method of proof that we do here, just to keep you in line. So what we can do is kind of introduce the notion of the subspace categories, that we use this cat with an index m of some subset of m, would be kind of the idea that we don't need to cover all of m, but just the subset that we are studying here inside of m. So this is kind of what's introduced there. And what you then do is to study this thing for sub-level sets, and then let the level set rise and rise and rise. And basically, you use Minimax methods. So kind of if you don't cross critical values, nothing happens. This is kind of the standard deformation lemma. But if you cross critical points, you can see that your category will increase. And so you can then basically count critical levels with this procedure, and using the nice Minimax methods to really show that something is happening there, so that this cat is really increasing. So this is kind of what you do there. The problem occurs if you study G-invariant functions on Hilbert manifolds with respect to some Lie group action. Because then, if you have G-invariant functions, you have critical points do not occur as singular isolated points, but as G-orbits. They always, of course, come in orbits. And if G is a Lie group, so this means that every orbit consists of infinitely many points. So this counting here is rather pointless. So what we would really like to count is the number of orbits and not the number of points itself. And doing this in a Nüstern-Schneermann way with this approach of sublevel sets and so on, and to work this out in such a way. And there has been already an approach. I mean, there are equivariant versions of Nüstern-Schneermann category. This was, I think, first done by Knapp and Puppe in the 80s. Then there's a nice Springer lecture notes volume by Thomas Bartsch, where he studies variational problems with symmetries in this way, so it generalizes many of these things. But this is something where these things work and you get some results, but still they create some difficulties or some things they cannot do. And what I want to do is to study, to suggest a different approach to this. Just first, before I do so, let me give an example. The main motivating example is the closed geodesics problem. Just, I think many of you should be familiar with this. I formulate this for Finster metrics. So let's say we have a closed manifold and we have a Finster metric. So from the tangent space to of a tangent bundle of M to the non-negative numbers. So if you don't know what a Finster metric is, it's kind of roughly, very roughly speaking, something like a norm on each tangent space. And for example, you could take the norm induced by a Riemannian metric on each fiber if you have a Riemannian manifold. So if you can think of Riemannian manifolds here throughout, so it's fine. Then you take the free loop space, which I call lambda m, but you don't take the continuous loop space, you take this H1 loop space. H1 from S1 to M, this or written as W1, 2 from S1 to M. This is a Hilbert manifold, which is locally modeled on the Sobolev space W1, 2 from S1 to Rn. So as soon as you go study Hamiltonian or Lagrangian action functionals, you will have seen this, or geodesics, and this is a standard. This is a Hilbert manifold. This is a subspace of the space of continuous loops, and it has a big advantage. It has the homotopy type of the space of continuous loops. So we're really not losing the topology. Topologically, we're not losing much when we go to this Hilbert manifold. On this Hilbert manifold, we have a function EF, where we simply integrate the norm along the loop, so we or the square of this Finster norm here. So we insert gamma and gamma dot into this Finster metric. So here would be in this Riemannian metric, you could think of the same thing here. Then take the square, and then take the integral once around the whole loop. So this is a function on this Hilbert manifold, and this has nice properties. Namely, this is C1, and it even has locally Lipschitz-bounded derivative, so it's continuously differentiable. It is S1 invariant with respect to the standard time shift action on the loop space. So if we just start the shift the time points, if we don't study the gamma, but gamma of t, but gamma of t plus s for some fixed s. So this parameter s, this is what we get as an S1 action here. And it was shown that this satisfies the Palais-Smale condition. I think in the Riemannian case, this was already known to Palais-Smale, but in the Finster case, this was shown by Mercuri in '77. And so this means, in principle, it has all nice things for the Nüstern-Schneermann approach. And the critical points of this thing, and this is now how why this is so interesting. The critical points of this EF consists of closed geodesics of F. If you don't know what this is for Finster manifolds, just take this as the definition for this talk. And we have constant loops which occur. So these, of course, come in families. So the constant loops form basically one big family of critical points, and so do kind of one closed geodesic comes already in an S1 orbit. And this is for this Schneermann approach, there's this problem. So the S1 orbits occur here. And for this we can come up with by using these equivariant versions of this Schneermann category. So this is kind of a way of counting orbits. But the second problem, this is now the problem for the other approach as well, namely this space of constant loops in M. This is a critical submanifold of lambda M. This has the same dimension as M itself, but we don't basically know when we count the orbits with the Schneermann methods. We don't know what this space, in which sense this contributes to this counting. So what does this do? How does this raise the number or not? So this kind of messes up our counting procedure when we use these this equivariant approaches. So the question is kind of how can we find an approach so that really both of these things are not problems anymore. And this is kind of how I started to do my construction here, then the so-called spherical complexities. I do this generally for not loop spaces, but maps from spheres to space X, so just sphere spaces, because the general construction works in every dimension. We have a topological space, and we take some number n, and I let Bn plus 1x denote the space of continuous n plus 1 balls, so just unit ball in Rn plus 1 here. And Sn of x to be the space of n spheres in X, but only those which are null homotopic. And spaces which are null homotopic, this is basically the same as saying that maps from spheres which can be filled by maps from balls. For every map which is null homotopic, you can find a map from the ball to X, which restricts to this map on the boundary. And this is now the idea, the starting point of it. So now, instead of motion planners, I search for sphere fillings. I take a subset of this space of non-homotopic spheres, A, and I want, on this set A, I want to have a map from A into this ball space here, so the space of n balls, which should be continuous, such that over each gamma, this is filled by a map which restricts to gamma itself. So the ball restricts on the boundary to gamma. So this is really indeed a filling, and that this happens continuously with respect to the C0 topologies here. So this is a sphere filling, and this I can now use to give a definition of invariance in a kind of TC style. I call them SCN, and then an index X, and of the set A. This is the smallest number R, such that I can cover A by R open subsets, such that over each of these subsets I have a sphere filling. So again, I could also do this again in sectional category, namely I can take a fibration which just goes from this ball space to the sphere space, namely just a restriction. This is a fibration. So then we get the sectional category, and so on, I get the whole machinery running. But this is kind of the explicit definition here. So I can cover this by sphere filling domains. Just if you take the whole space, so just the whole Sn of X, this is then called the n spherical complexity of X. But these numbers are a bit disappointing because kind of they are almost always infinite in most cases. So they are not really interesting, but these subspace ones are really interesting. Just as a remark, this is really connected to TC. Namely, if we take n equal to 0, this would be B1X. This would just be the maps from the interval to X, so the path space. And here we would have the maps from S0 to X. S0 is 2 points, so this would just be X times X, which means this really gives, again, the proper definition of TC. So this is, again, the standard definition. This really generalizes TC to higher dimensions in some sense. So properties of these things. If you have a metrizable absolute neighborhood retract, and so we can think of a locally finite CW complex or a nice Hilbert manifold or a nice, anyway, but a nice space. So first of all, we have this constant map problem. So we have this map Cn, which takes each point to the constant map from the sphere to the point. This would be the generalization of the notion of constant loops. If we take the whole space, or the whole image of this map, so Cn of capital X, it turns out that this sphere filling, this is spherical complexity, really counts this as 1. So this can really be covered by one domain, and the proof fits within one line. I think I haven't included this, no, but with each constant sphere, we associate a constant ball, I think, to the same point, and we're done. This is everything. So that's very, very simple. So this is a good news. So this means if I have these new invariants, they disregard this, so we don't have to care about these constant things anymore. They are just counted as 1. Now we have to see what happens with group actions. And on the n-dimensional case, we always have group actions, but this time a bit more complicated. We have actions of O(n + 1 on these spaces, simply by inserting into the sphere the parameter, which is an element of the sphere or of a ball more generally. We just multiply this sphere from this parameter of the inside by a to the -1. Just included the -1 here to make it a left action. But just by reparametrization. So we just multiply the parameter by some orthogonal matrix. So this gives a group action on these sphere spaces and ball spaces. And it turns out that, so if we take some subgroup of O(n + 1 and take the restriction to the G action, and that G gamma denote the isotropic group of an element gamma here of the sphere space, then there are two conditions under which it behaves nicely, namely either if the isotropic group is trivial, or if we're in the one-dimensional setting, then we don't need any restrictions on the isotropy. Then we get that one whole orbit, the whole G orbit of gamma, is also counted as 1 by this spherical complexity. So both problems are solved. The constant maps are just counted as 1, and each orbit is counted as 1. So we are really good for our counting procedure. Just for the case that the isotropy is trivial, and you can also write down the proof in one line, we can just take we start with the element gamma, which is a map from the sphere. We just take an arbitrary continuous map from the ball, which restricts to gamma. And then as we rotate or move gamma with the A, we just move beta with A as well. And since the isotropy is trivial, nothing can happen. So this is really well defined. And so this is the way how can we define such an S and then extend it continuously to an open neighborhood of the orbit. So this is very straightforward. And for the for the one-dimensional case, the thing is that all interesting isotropy groups are either the whole group or they are finite. And with these finite groups, you can work out with them and really kind of figure this out. Okay, and then we get some Lüsternig-Schneeremann type results, but since I'm running out of time, I will just go quickly through the general results. So we can get some counting of G orbits of G invariant functions on Hilbert manifolds inside these sphere spaces. And this is here the crucial thing. The spherical complexity of a sublevel set A is then the lower bound for the number of G orbits of this function f inside the sublevel set plus 1. This additional plus 1 is the contribution of the constant maps that we had before. So this is just I'll just quickly go through this, and then I go to the closed geodesics. Here I can really formulate this lower bound for the closed geodesics. So I take the energy functional, apply this to the energy functional, and take SO2 orbits of contractible closed geodesics. So I can only study contractible curves in this way. Then I get that the number of contractible closed geodesics of energy at most A is bounded from below by the sectional spherical complexity of this sublevel set -1. And the same holds for O2 orbits if the Finster metric is reversible. This basically means that the functional is then also O2 invariant, as it is for Riemannian manifolds, and then we get the same result for the O2 orbits of contractible closed geodesics. Only the problem is here that this counting does not distinguish iterates of the same geodesic. As you know, from the phenomenon of closed geodesics, if you have one closed geodesic and you iterate this, so you kind of run through the same geodesic at double speed and do this twice, you get again a geodesic, and the same do for multiple periods. So this counting does not distinguish these iterates. So you cannot see if they are iterates or not. But still, we can use this to get some nice results. Maybe I can quickly go through this. So the results on closed geodesics, the existence of closed geodesics is still not completely clarified yet, how many and for which metric. So for the Finster case, we can say, first of all, it's from the theorem of Lüsternig and Fitch from 1951, which was stated for the Riemannian case, but the proof goes through line by line to the Finster case, that every Finster metric on a closed manifold admits a non-constant closed geodesic. Then we want to study how many geometrically distinct ones are there. So distinct ones, very roughly spoken, they are not geodesics that do not lie in the same orbit and that are not iterates of one another. So really different, just visually different closed geodesics, how many you have inside a manifold. And this is still not clarified yet. I have some recent results for Finster metrics. First of all, the big famous result by Bangert and Long from 2007. They have shown that the two-sphere, there every Finster metric has two positively distinct closed geodesics. So two distinct ones here. Then in 2009, it was shown by Rademacher that every bumpy Finster metric has two positively distinct ones. This is a generic condition here. Basically, it's a more spot condition for the energy functional. Then there are certain results for the three-sphere and for pinched metrics on the n-sphere by Long and his collaborators, so Long and Duan, and by Wang, and there are some other papers basically with the same author names. And I was then able to show also a theorem, because I'm just presenting you part of what I did. So if we have a closed-oriented manifold, with let's assume we have this case, we have a Finster metric here of so-called reversibility lambda. This is basically some parameter which measures the symmetry or asymmetry of the Finster metric. Just keep in mind, in the Riemannian case, it's very symmetrically, this is equal to 1, and if not, it is bigger than 1. So this is just some constant which is 1 or bigger, which has flag curvature k. And flag curvature is just the generalization of sectional curvature to the realms of Finster metrics. So let LF be the length of the shortest non-constant closed geodesic of F. And then I found some conditions, namely, if we are, so I first studied spheres. So if you're an even-dimensional sphere, which is of dimension 4 or bigger, if we have positive flag curvature, which is bounded from the world by 1, and if there's an inequality between the Finster metric and G1 is the standard round metric, so the constant curvature 1 metric on this on the 2D sphere. If we have this inequality here, which so that f is smaller than or equal to 1 over, plus lambda over lambda, so this equals 2 if lambda is equal to 1, so in the reversible case. If there's an equality in between these two metrics, then there are two positively distinct closed geodesics of length at most. So the second one is less than twice as long as the first one. This is what we get here. There's a result from the odd-dimensional case, which is slightly more complicated conditions, but we also get here. And we get a simple result for complex projective and quaternion projective spaces, where we also have basically the same conditions as in part A, only that we have to replace this round metric by the standard globally symmetric metric here, where closed geodesics, prime closed geodesics have length through pi. then we also get two positively distinct closed geodesics of length smaller than twice the length here. So this is this is kind of the interesting thing is also that you get this length bound, because it's kind of the methods that long analysis collaborators are using. You can get existence, but you get no bound on the length whatsoever. So the closed geodesics you can predict with this method can be very long, and so I could then put this length bound here on top. Okay, so this is the closed geodesic result, and this is basically all I wanted to tell. I've included now a few slides with some literature. Of course, I don't expect you to copy this right now, but I think since the slides are uploaded, this you can then read up. This basically contains all the manuscripts that were used in the second part and that I referred to in the different, in these different issues. And so thank you for your attention. And if you want some more video talks, there was this online conference I mentioned also earlier by the Beer Station. They have an online workshop. They had an online workshop on topological complexity, and all the videos of this one are now online on this website here. And these also, I think, also almost all the topics that were contained in the second part here, there were also talks about these topics here in this Beer's workshop. So you can then watch these talks there and then see maybe some more details if you want, and about some other recent topics on topology. Okay.